55 kilometers. That's the distance separating Hong Kong from Zhuhai and Macau, three of the most economically vital cities in Asia. For centuries, this stretch of the Pearl River estuary remained an uncrossable barrier. Ferries took 4 hours. Trucks drove 200 kilometers around the bay. The cost to commerce? Billions lost every single year. Then, China did what many engineers said was impossible. They built a highway across the open sea. The Hong Kong-Zhuhai-Macau Bridge, the HZMB, is not just a bridge. It's 3 cable-stayed mega-bridges, 2 artificial islands constructed from nothing, and the world's longest undersea highway tunnel. Combined, they formed the longest sea crossing ever built by humanity. The price tag? $20 billion. The timeline? 9 years of relentless construction. The workforce? Over 14,000 engineers and workers at peak operation. This is the story of how China conquered the ocean, one impossible engineering challenge at a time. Before a single pile could be driven into the seabed, engineers faced a logistical nightmare of unprecedented proportions. The Pearl River estuary isn't calm water. It's one of the busiest shipping channels on Earth, handling over 4,000 vessels daily. Shutting it down? Not an option. The solution required military-level coordination. Construction crews established floating command centers positioned strategically across the 35-kilometer marine section. Every barge, crane, and supply vessel operated under a centralized Building Information Modeling System, BIM, that tracked over 10,000 moving components in real time. But the real challenge lay beneath the surface. Marine geologists conducted over 1,200 seabed surveys across the route. What they found was troubling. The estuary floor consisted of soft alluvial deposits, silt and clay sediments accumulated over millennia. In some locations, this unstable layer extended 40 meters deep. Building on it directly would be like constructing a skyscraper on quicksand. Before foundation work could begin, engineers deployed specialized dredging vessels to excavate these weak sediments. Over 100 million cubic meters of this sediment was removed and transported to designated disposal sites, enough to fill 40,000 Olympic swimming pools. Simultaneously, environmental teams faced an extraordinary constraint: the Chinese white dolphin. These endangered mammals, fewer than 2,500 remaining, call these waters home. Construction could not proceed without protection protocols. Underwater acoustic monitoring stations were deployed across the site. When dolphins approached within 500 meters, pile driving operations automatically suspended. Bubble curtains, continuous streams of compressed air, created sound barriers, reducing underwater noise by up to 90%. Nature and engineering would coexist, but only through relentless planning and real-time adaptation. With the seabed prepared, the true engineering began. The HZMB required over 1,100 individual piles driven into the ocean floor, each one a feat of precision engineering in its own right. These weren't ordinary piles. The largest measured 2.5 meters in diameter and extended over 100 meters in length, taller than a 30-story building. Each one weighed upwards of 500 tons. Positioning them accurately in open ocean with currents, waves, and wind constantly shifting required GPS-guided pile-driving barges accurate to within 50 millimeters. The pile-driving rigs operated around the clock, hydraulic hammers delivering 1,200 kilojoules of force per strike drove the steel casings through the soft sediment until they seated firmly into bedrock, sometimes 90 meters below sea level. Once positioned, the hollow piles were reinforced with massive rebar cages, interlocking networks of steel reinforcement bars, some weighing upwards of 100 tons. Lowering these cages into the submerged piles required synchronized crane operations with millimeter precision. A single misalignment could compromise the entire foundation. Finally, high-performance marine-grade concrete was pumped into each pile. This wasn't standard concrete. Engineers developed a proprietary mix designed to cure underwater, resist saltwater corrosion, and maintain structural integrity for 120 years, the bridge's designed lifespan. Over 400,000 cubic meters of this specialized concrete would eventually be poured, enough to construct 15 Empire State Buildings. But the foundations were only the beginning. 2 artificial islands awaited, and they would be built using a technique never before attempted at this scale. Here, in the middle of the Pearl River estuary, engineers would create land where none existed. Not by traditional methods of dredging and dumping, which would have taken years and devastated marine ecosystems. Instead, they employed a revolutionary technique: the steel cylinder island. 120 giant steel cylinders, each 22 meters in diameter and up to 50 meters tall, were prefabricated on shore. These hollow giants, weighing up to 550 tons each, would become the island's perimeter wall. Installing them required the world's largest floating crane, a 12,000-ton vessel capable of lifting and positioning each cylinder with centimeter accuracy. One by one, the cylinders were lowered through the water column and vibrated into the seabed using high-frequency hydraulic hammers. In just 7 months, a time frame that stunned the global engineering community, both artificial islands took shape. The traditional method would have required 4 years. With the islands complete, attention turned to the bridge spans themselves. The HZMB features 3 signature cable-stayed bridges, each with distinctive tower designs symbolizing Chinese cultural heritage. The Zhuzhou Navigation Channel Bridge features sail-shaped towers. The Qingzhou Channel Bridge showcases elegant Chinese knot towers reaching 163 meters skyward. Constructing these towers required jump-form systems, self-climbing formwork platforms that advance vertically as each concrete section cures. Every 4 days, the forms would hydraulically lift to the next level, allowing continuous around-the-clock construction regardless of wind or weather. But the true engineering marvel lay beneath the waves. The Immersed Tube Tunnel. At 6.7 kilometers, the HZMB Tunnel is the world's longest undersea highway crossing. 33 individual tunnel elements, each measuring 180 meters long, 38 meters wide, and weighing 80,000 tons, had to be fabricated, floated, sunk, and joined together on the seabed with absolute precision. Each element was constructed in dry docks on Guishan Island, then floated out to sea using calculated buoyancy. Tugboat convoys guided these monstrous segments, longer than aircraft carriers, through congested shipping lanes at a crawling pace of 4 kilometers per hour. Sinking each element required flooding its internal ballast tanks, while 1,200-ton anchor blocks on the seabed provided positioning guides. The tolerance for placement? 20 millimeters. Any deviation larger than a human finger width would compromise the watertight seal. The final connection, joining element 33 to complete the tunnel, became a media sensation. After 12 failed attempts due to siltation and current interference, engineers achieved what many believed impossible: a perfect seal, 12 meters beneath the open ocean. The South China Sea doesn't tolerate weakness. Every year, an average of 6 typhoons track through the Pearl River Delta, bringing sustained winds exceeding 200 kilometers per hour. The HZMB had to survive them all. For over a century, engineers subjected every design element to exhaustive wind tunnel testing. The bridge deck features aerodynamic fairings, curved shields beneath the roadway that channel wind smoothly underneath rather than creating destructive vortices. The cable stays incorporate helical strakes, spiral protrusions that prevent dangerous oscillation, known as vortex-induced vibration. But wind wasn't the only threat. The region sits along active seismic zones. The HZMB is designed to withstand a magnitude 8.0 earthquake, a catastrophic event that could level entire cities. Massive seismic isolation bearings, weighing up to 50 tons each, sit between the bridge deck and its support towers. During an earthquake, these devices allow controlled horizontal movement of up to 600 millimeters, absorbing destructive energy rather than transmitting it through the structure. Inside the tunnel, safety systems reach another level entirely. The immersed tube sections are joined using Gina gaskets, massive rubber seals compressed between adjacent elements by the immense water pressure above. These gaskets, developed for the most demanding offshore applications, create watertight connections capable of withstanding decades of saltwater exposure and seismic movement. The tunnel features dual-bore design, 2 separate roadways with a central emergency corridor. Every 125 meters, cross passages allow evacuation between tubes. Fire suppression systems can extinguish vehicle fires in 90 seconds, and AI-powered monitoring cameras continuously analyze traffic flow, detecting accidents and triggering response protocols before human operators even recognize the threat. 40,000 sensors embedded throughout the bridge and tunnel continuously report structural health data: strain, vibration, temperature, corrosion rates. This digital nervous system ensures that engineers will detect problems decades before they become dangerous, keeping the HZMB safe for the next century and beyond. On October 24, 2018, after 9 years of construction, the Hong Kong-Zhuhai-Macau Bridge opened to traffic. The results were immediate and transformative. A journey that once took 4 hours by ferry now takes 30 minutes by car. The 200-kilometer detour around the bay? Eliminated. The 3 cities, Hong Kong, Zhuhai, and Macau, effectively merged into a single 1-hour economic zone containing 70 million people with a combined GDP exceeding $1.5 trillion. Zhuhai's property values doubled within 2 years. Manufacturing facilities that once bypassed the region now establish headquarters there. Tourism between the 3 cities exploded. The Greater Bay Area, China's answer to Silicon Valley, became a reality, with the HZMB serving as its central artery. But the bridge's legacy extends beyond economics. The engineering innovations pioneered here, rapid artificial island construction, precision immersed tunneling, AI-integrated structural monitoring, have influenced megaprojects worldwide. The techniques developed for the HZMB are now being applied to crossings in Turkey, Denmark, and South America. For China, the HZMB represents something more: proof that the nation can achieve what others deem impossible. This single structure required innovations in marine engineering, material science, environmental protection, and logistical coordination that pushed the boundaries of human capability. 55 kilometers of steel and concrete, 120 years of designed service life, $20 billion invested in a vision of connectivity. The Hong Kong-Zhuhai-Macau Bridge didn't just connect three cities. It proved that when engineering ambition meets national determination, even the ocean itself can be conquered.